Good morning. I thought I would start adding a little intro to my videos, simply to show my face. So today we are going to be starting on Chapter 5, which dives into the MOSFET, the Metal-Oxide-Semiconductor Field Effect Transistor. And we're going to essentially go through the first, fourth of the chapter or so. This is Chapter 5 in the Sedgwick and Smith textbook. And that's going to take us through the basic structure of the Metal-Oxide-Semiconductor Field Effect Transistor, as well as how it operates when the voltage across the drain and source terminals is very small. And we'll pick up next time diving into a more general description of how the device works in its triode region. Good afternoon. We are going to jump into Chapter 5 today, which deals with MOSFETs, or Metal Oxide Semiconductor Field Effect Transistors, from the usual textbooks, Sedgwick and Smith. And this is the first type of transistor that we are going to talk about. We'll be talking about two, this and the bipolar junction transistor. So in this chapter, we're going to learn about the physical structure of the MOS transistor and how it works. We're going to learn how the voltage between two of the terminals, this is a three-terminal device, between two of the terminals controls the current flowing through the third, and the equations that describe these VI characteristics. We're going to learn how the transistor can be used to make an amplifier, as well as a switch for digital circuits, or actually for analog circuits. And this is actually a really interesting chapter because I think building an amplifier using a transistor shows us the inner workings of those black boxes that we're used to using, those chips. We're going to learn how to obtain linear amplification from the fundamentally nonlinear MOS transistor. And we're going to learn the three basic ways for connecting a MOSFET to construct amplifiers with different properties. We're also going to dive into some other practical circuits for MOS transistors that can be constructed using discrete components. So far we have studied two-terminal semiconductor devices, primarily the PN junction, the diode. However, now we're going to turn our attention to three-terminal devices. They are more useful because they present a multitude of applications, more so than the diode. And examples include signal amplification, digital logic, memory, etc. Now, in the simplest terms, what is the desired operation of a three-terminal device like a MOSFET? Ideally, it would employ the voltage between two of the terminals. I said this previously, but employ the voltage between two of the terminals to control the current flowing into the third. So the way you can think about it is, you are able to control the voltage here. And that would then define how much current flows along that path. So almost like a knob, right? That we could turn up and down, and that would increase and decrease the current flowing along that path. Now, what are the two major types of three-terminal semiconductor devices? There's the Metal-Oxide-Semiconductor Field Effect Transistor, MOSFET, or the bipolar junction transistor, BJT. Now, the MOSFET is more widely used in the implementation and design of modern electronic devices. We'll talk about some of the reasons why. The bipolar junction transistor is the earlier technology. It was developed first. Why are MOSFETs more widely used? They are smaller. They can be, size is one major component. They are easier to manufacture, and they use less power. And we'll see in this chapter why this is the case. All three of these bullets. MOSFET technology allows the placement of approximately 2 billion transistors on a single integrated chip. Now, this number I have not updated in several years, essentially since I first started teaching the class. I'm sure that number is much higher now, but actually it changes every year. So I'll put a little plus there. 2 billion plus transistors on a single IC. And it's the backbone of VLSI technology, very large-scale integration technology. It's considered preferable to BJT technology for many applications. We're going to learn about the bipolar junction transistor more in Chapter 6. And we'll have an opportunity to do some compare and contrast between those technologies. So figure 5.1, which is shown here, gives us the general structure of the N-channel enhancement type MOSFET. And we'll talk about what this means, N-channel versus P-channel, enhancement versus depletion type MOSFET. So the general structure is shown here. For the N-channel, we have a P-type substrate, which is essentially just the body of the MOSFET, a big piece of P-type doped semiconductor. We have two wells that are dug into it and filled with the opposite type, N-type doped semiconductor material. Both of those wells have an attached lead. One is called the source, one is called the drain. And then here we have this two-layer piece. So up top, we have a metal connector. And the middle, which I'm coloring in with red, is a dielectric material. In this textbook, we'll generally talk about silicon oxide, but there are others that could be used. And so what that does is it separates the lead connected here, the gate, from the body of the MOSFET. And so what that means is, we'll see this more later, is that no current can flow from the gate into the body of the substrate. It's like a capacitor almost, right? Where down here is the body of the MOSFET and up here is the gate terminal. For DC applied voltages, right, this will act like an open circuit, not allowing any current to flow. Now this obviously will be different for AC, but let's focus on DC for the moment. Down here we have the body connector. This is not always included in all devices. You won't always have a fourth terminal, but some will. Now, one additional thing I should point out, an important characteristic of a MOSFET, is this right here, the thickness of the dielectric layer that separates the gate from the body, and this will come into play later and will affect how the MOSFET works. Okay, so you can see here there's some additional highlights. Again, we have the two doped regions. We have the layer of silicon oxide that separates actually this should say the gate and the body. And then the metal plate on top of the dielectric material that forms the gate electrode. And then we have one P-type doped region down here. Okay, the name MOSFET is derived from its physical structure. Metal oxide, that's this part down here, semiconductor, field effect transistor. And field effect, we'll see what that means in a second. Essentially here, we are going to generate an electric field that is going to affect how the transistor works. So metal oxide semiconductor, and then field effect, electric field effect transistor. However, many MOSFETs don't actually use any metal. They use a polysilicon instead. This has no effect on the modeling or operation as described here, but it's just a disclaimer that I wanted to make. Another name for the MOSFET is the insulated gate FET or IG FET. Now you'll see that the device is composed of two PN junctions. However, they maintain reverse biasing at all times. The drain will always be at the positive voltage with respect to the source. So what am I saying right here? If you look at the basic structure of the MOSFET, there really is no distinction between the positive and the negative terminals, or what the polarity, expected polarity across the MOSFET is. And so it doesn't matter. You can switch them. They are interchangeable. Normally, we assume that the positive end, we'll call that the drain, and then the negative end, we'll call it the source. And then if you're applying an AC voltage, right, then those values don't have as much of a meaning. So, Okay, next slide. So with 0 voltage applied to the gate, I said this a little bit on the previous slide. We talked about the 2 back-to-back diodes. So you can see here, as shown in the red, the wells combined with the body, they essentially form 2 p-n junctions, right? Because any place where the p and the n-type dope semiconductor meet forms a junction, we have a p-n junction. And so they are back-to-back diodes, meaning that in this state, no current can flow from here to here, right? Anytime we have back-to-back diodes, there's no current conduction. This yields a very high resistance between the drain and the source terminals initially, somewhere in the range of 10 to the 12 ohms. Now, we need to talk about, well, going back here for a second, right? The MOSFET in this configuration is not very useful to us. It doesn't conduct any electricity, so what? So now let's talk about what happens if the source and drain are grounded and a positive voltage is applied to the gate. So we have a ground here, we have a ground here, and now we are applying a voltage VGS, S is ground anyway, to the gate. We want to see what happens when we do this. So the first thing that happens, so we apply our voltage VGS to the gate terminal, causing a positive buildup, or a buildup of positive charge along the metal electrode. So let's take a look at that one more time. You can see there's a little bit of a mini animation here, right? The VGS will supply positive charge, which will build up along the electrode associated with the gate. Now, this buildup causes the free holes, again, this is a p-type substrate right here. So inside of the p-type substrate, there's going to be a lot of holes. And this causes those holes to be repelled from this region directly underneath, well, the area that's shown in the white. So again, I'll show this one more time. You can see, again, the repelling of the holes that originally were in this area. Right? They get pushed down further because, right, the positive charges right here repel the charges of the similar sign. Now, step 3. This migration, meaning the positive particles, the holes moving downward, results in the uncovering of negative bound charges that were originally neutralized by the holes. And so we've talked about this topic of bound charges before. You should be familiar with the characteristics of those bound charges. And so now, in the area, again, that was originally in the white that I had shaded earlier, we have a whole bunch of these negative, uncovered bound charges. Now, the positive gate voltage also will attract electrons from the N source right here and pull them into the center. And that's what we see in this second part of the animation. We see additional negative charge carriers that are pulled into what we call the channel. And so the channel is essentially this area in between the two wells. Now, once a sufficient number of these electrons, these charge carriers accumulate, what we will see is that a pretty concrete, again, I'll draw it here, channel of N-type charge carriers forms between the two wells. So this area now begins to look the same as the wells themselves. And this connects the source and the drain regions to one another. And as you can imagine, now this is going to allow current to flow between the drain and the source. This induced channel is also known as the inversion layer. Okay, So now there's a couple of terms that we need to discuss, and those are highlighted here in blue. So one is called the threshold voltage, V sub T. This is the minimum value of VGS. Remember that it's the voltage VGS here that is controlling, or that is creating our electric field, which is then repelling the charges, the positive charges, pulling in the negative charges, and then causing our inversion layer to form. So when VGS is equal to 0, there's no inversion layer. As it grows, so does the tendency to form the inversion layer. Now, that doesn't happen immediately. There is a minimum value of VGS that's required to form a conducting channel between the drain and the source, and normally this is somewhere between 0.3 and 0.6 volts. Field effect. So in the name, it's called the Metal-Oxide-Semiconductor field effect transistor. What does field effect stand for? Touched upon this a little bit, but just to reiterate, when a positive value of VGS is applied, now remember this is for this specific type of enhancement type MOSFET. So it could be negative, but we're not going to get into that yet. So in this case, when a positive value of VGS is applied, an electric field develops in between the gate electrode and the induced end channel. The conductivity of this channel is affected by the strength of the field. The stronger the electric field is, the lower the resistance, or the higher the conductance will be between the drain and the source terminals. And so the SiO2 layer acts as the dielectric, a lot like how a capacitor works, and allows us to generate this electric field. The effective, or the overdrive voltage, is the difference between the VGS we apply and VT. So overdrive voltage is the component of VGS that actually starts to induce the inversion layer. This value is always greater than 0. And what that means is that when VT is greater than VGS, the overdrive voltage is just assumed to be 0. It doesn't have any meaning as far as a negative value of overdrive doesn't have any meaning. Okay, for our purposes. Another value that we have to be concerned with is called the oxide capacitance, and this is the capacitance of the parallel plate capacitor, this piece here. Okay. Per unit gate area, and that's given by equation 5.3. I'm sorry for the 644 thing. I went and removed that from most of the slides. I must have left one on here. I went through and removed all the I changed the equations to a form that is compatible with the iPad. So anyway, the oxide capacitance is going to be equal to the permittivity of silicon oxide, which is normally 3.45 times 10 to the negative 11 farads per meter. And then this is the thickness of the silicon oxide layer in meters. I'm sorry, it looks like I did not do a very good job of getting rid of these numbers. I will try it again before next lecture. I converted everything to a JPEG, but I guess it didn't stick. So moving on to this question here, what is the main requirement for an N channel to form? So the voltage across the oxide layer must exceed VT. Going back to here, right, it means that the overdrive voltage has got to be greater than 0. So for example, when VDS is equal to 0, and that's what we're looking at now, both the drain and the source terminals are grounded, the voltage at every point along the channel is equal to 0. And so the voltage across the oxide layer is uniform and equal to VGS. Right, when both of these are grounded, that means that the voltage along this entire area right here is going to be equal to ground. And that means that the difference between this point and here and here and here and here and here, that voltage difference is all going to be the same. It's going to be equal to VGS. Now, we want to start to put this in terms of a VI relationship. So, and the intermediate step in doing that is to define the amount of charge that's stored in the inversion layer. So how can we express the magnitude of the electron charge contained within the channel or within the inversion layer? And that's done by equation 5.2. So the magnitude of the charge is equal to the oxide capacitance times the width times the length of the channel times the overdrive voltage, and the result is in coulombs because we're talking about charge. What is the effect of the overdrive voltage on the N channel? We've already said this several times. As VOV grows, so does the depth of the N channel, as well as its conductivity, as well as the amount of charge that's stored within it. All of those values are proportional to one another. Now, we are going to slowly build up to larger and larger values of VDS. So let's start off. Initially, we had VDS was equal to 0. Now we're going to move to the next step, which is applying a small VDS, and then the next step is going to be VDSs that are much, much larger than 0. So once VGS is applied, and you have to be careful here. I know that they sound very similar, right? VDS, VGS, but they are very different values, right? VGS, the gate source voltage, acts as the, if you remember the analogy we used in the very beginning, this is essentially the knob that turns up and down the current flow. Okay, VDS, this is the voltage across the path where current flows. Okay, and so this would be the actual current, the actual voltage that induces the current. This voltage down here simply changes the resistance. So I don't want to go too much into this topic because we are going to talk about it more. So anyway, so now once VGS is applied, a channel for IDS exists, our inversion layer exists, and as such, one expects that if we apply VDS, current will flow. I mean, you could think about it like almost like a variable resistor. VGS is going to turn down the resistance, and VDS is going to cause current to flow because IDS, which is here, is equal to VDS over whatever the resistance is, and the resistance is a function of VGS. So first we're going to consider the cases where VDS is small, 50 millivolts or less. Really sorry about these numbers. I spent a decent amount of time trying to fix this. For small values of VDS, how does one calculate the current ID or IDS? And so for that we use equation 5.7. And so what we see is that ID is equal to COX, which is the oxide capacitance, times the width of the channel, times the overdrive voltage, times, I'm just rewriting it so because part of it is covered up by this chunk here, times a value called mu n. Well, we've already learned about what that is. That's the electron mobility, times the voltage between the drain and the source, divided by the length, and that is in amps. So as we would expect, the current flowing through this transistor is going to be proportional to the overdrive voltage as well as the value of VDS. Okay, so how does one calculate charge per unit length of the N channel? And this is important because it's going to come into play later. And it's going to help us move on to that next step, which is talking about when VDS is significantly greater than 0 or greater than this 50 millivolt range that we are looking at right now. So for small values of VDS, we can still assume that the voltage between the gate and the N channel is constant along its length, right? If you remember, we have this dielectric material, we have the gate. Okay, so actually that's the dielectric material. And so the voltage between here and here, here and here, here and here, here and here, along the whole channel, that's going to be the same. And therefore, equation 5.2 from 2 slides back applies. Now, so what we're going to do is use this equation 5.2, and we are going to move this to the other side to calculate the charge per unit length as shown in equation 5.4. So we had charge stored in the inversion layer. Now we're going to normalize that by length, which gives us charge per unit length in coulombs per meter. Okay, now we want to calculate the electron drift velocity for this case here. And for that, we're going to use some equations that we've seen before. 5.5 tells us that the electric field across the channel is going to be equal to the VDS value applied divided by the length of the channel in volts per meter. And the electron drift velocity is going to be equal to the mobility times that electric field strength, which is given here. Like any velocity, it's provided in meters per second. Now, note that two values may be employed to define the current in amperes. We need to combine this with this down here. Actually, not this one, with this one down here. Because you can see if we have coulombs per meter and we multiply that by meters per second, we are going to end up with coulombs per second, which is equal to amps. And so when we multiply those two together, we end up with this value of the current ID as shown here. The current is equal to electron mobility times oxide capacitance times width of the channel divided by length of the channel times the overdrive voltage times the voltage between the drain and the source channels in amps. Now, what is this other version of the equation down here? 5.8a. All it does is put this in terms of a resistance. So if we took this value, so if we took this VDS and then we took this ID and we created VDS over ID, that would give us the equation below, which is what we're going to call the drain source resistance equal to VDS over ID, and that's equal to 1 over electron mobility, oxide capacitance, width of the channel, length of the channel, overdrive voltage. Now, I know I've apologized for these numbers several times, but remember that you can check the version of the notes online, which is a PDF, and look at those as we go through the video. And those do not have the numbers. Fortunately, I was able to clear those up for the PDF version. Okay, now this equation right here is very important. Actually, both of these are very important. Note that this overdrive voltage value represents the depth of the N channel. Okay, right here. Now, what if it's not assumed to be constant? how will this equation change? And we're going to be talking really about the shape of the channel. Right now, if I were to draw this, so I have my channel, I have my dielectric layer, I have my plate, I have the gate terminal, I have the well, I have the other well. Sorry, I'm running out of space. That'd be my drain, that'd be my source. So source, drain, gate. Now, this right here is a rectangle. And the reason is because the strength of the electric field over here is the same as the strength of the electric field over here. If the voltage VD, the voltage here starts to differ from the voltage here, the strength of the electric field will not be uniform going all the way across, and we will begin to see these change. They will not always be the same. Okay, so now taking one step back and talking about that value of RDS, what three factors is RDS dependent on? One is something called the process transconductance parameter, which is simply just the combination of the mobility and the oxide capacitance. And be careful because there's going to be two versions of this. There's going to be the process transconductance parameter, and then there's also going to be something we call the device transconductance parameter. I'll talk more about that later. There's the aspect ratio of the channel, which is the width divided by the length. And then there's the overdrive voltage, which we've already spent a lot of time talking about. So now this graph here, on the x-axis we have VDS, on the y-axis we have ID. And what we see is that when we have low resistance, that corresponds to a high value of VOV. And when we have high resistance, that corresponds to a low value of VOV. And so you can see the varying levels of resistance RDS that you can acquire by changing the overdrive voltage value. Now, I said I would tell you about the device conductance parameter, transconductance parameter, so that's actually shown here. So what you'll see here is that, taking one step back for a second, right, this device transconductance parameter, Kn, is equal to W over L times Kn prime, which is equal to W over L times mu n COX. So this is the process transconductance parameter. This is the device transconductance parameter. And the only difference between the two of them is whether they're multiplied by the aspect ratio or not. And then in terms of representation, is just the prime. So now what happens to ID when VDS increases beyond the small values? Remember we said we were going to move on to the next step where VDS is much, much greater than 0 or is greater than 50 millivolts. The relationship between them ceases to be linear, and what that means is for larger values of VDS, we're no longer going to be able to define this nice resistance RDS value, right? Our resistance implies a linear relationship between V and I, which we're not going to have anywhere beyond those very small values. So how can this nonlinearity be explained? And this is going to be a transition between today's lecture and the next lecture. I'm going to stop a little bit earlier than I would normally for two reasons. Number one is this is a really good transition point between this lecture and the next. And also, like I've said several times, I want to get this issue with the equations cleared up. So how can this nonlinearity be explained? If we assume that VGS is held constant at a value greater than VT, meaning that VOV is greater than 0, and we assume that a value of VDS is applied and appears as a voltage across the N channel, the inversion layer, we'll see that the voltage decreases from VGS at the source end of the channel to VGD at the drain end, where these two equations apply. But I think a picture does a better job of showing what's going on. This is the last slide we're going to look at today. What you'll see here is that when we start to apply a value of VDS, the strength of the electric field between here and here is going to be less than the strength of the electric field between here and here. And so what the result is that the depth of the inversion layer is going to be greater on this end as compared to this end over here. So as the shape of the N channel or the inversion layer changes, so will the amount of charge that's stored within it, and so will the VI relationship that we have observed. So we'll stop there. We'll pick up next time talking about the MOSFET for the case where VDS is greater than 50 millivolts. This is going to be part of the triode region of operation. We haven't used that term yet, but we'll talk about it next time.